Imagine this. You've poured your heart into writing a Java program. You've spent countless hours meticulously crafting each line of code, ensuring that every function and method works seamlessly together. The logic is sound, the structure is clean, and you feel a sense of pride in what you've created. It's elegant, it's efficient, it's about to crash. Just when you think everything is perfect, an unexpected error rears its ugly head. Why? Because somewhere in the intricate dance of your code, something unexpected occurred. An exception. These exceptions can be elusive, hiding in the shadows of your otherwise flawless code. Exceptions are events that disrupt the normal flow of a program. They are like uninvited guests at a party, causing chaos and confusion. They can occur for various reasons, from attempting to access a non-existent file to encountering an unexpected input value. Perhaps a user entered a string when your program expected a number, or maybe a file your code relies on has mysteriously vanished. Ignoring them is like ignoring a flashing warning light on your car dashboard. You might get away with it for a while, but eventually it will catch up with you. The consequences can be dire, leading to program crashes, data corruption, or worse. That's where exception handling comes in. It's not just a good practice, it's a necessity for robust and reliable software development. It's Java's way of providing a safety net, a mechanism to gracefully handle these unexpected events, preventing your program from crashing and burning. Think of it as a safety feature in a car that helps you avoid obstacles and stay on course. Instead of letting your program come to a screeching halt, exception handling allows you to catch these errors, handle them appropriately, and potentially even allow your program to continue running smoothly. It's like having a contingency plan for every possible scenario. It's about building resilience into your code, ensuring that it can withstand the unexpected and emerge stronger on the other side. By embracing exception handling, you are not just fixing errors, you are fortifying your code, making it more adaptable and robust in the face of unforeseen challenges. So, the next time you sit down to write a Java program, remember to embrace the unexpected. Plan for it, handle it, and let it make your code better. Because in the world of programming, it's not just about writing code that works, it's about writing code that thrives. And that, my friends, is the true essence of mastering Java, embracing the unexpected and turning it into an opportunity for growth and improvement. Exception handling is a powerful mechanism in Java that provides a structured approach to dealing with runtime errors. These errors, also known as exceptions, can occur for various reasons and can disrupt the normal flow of your program. Think of exception handling as a safety net for your code. It allows you to define blocks of code that might throw exceptions, the try block and separate blocks of code that will handle these exceptions if they occur, the catch block. This separation of concerns is crucial. It keeps your error handling logic distinct from your main program logic, making your code cleaner, more readable, and easier to maintain. But exception handling is more than just catching errors. It's about gracefully handling them. This might involve logging the error, displaying a user-friendly message, or attempting to recover from the error in a way that allows your program to continue running. By anticipating and handling potential errors, you transform your program from a fragile house of cards into a robust and reliable application. In the realm of Java, not all exceptions are created equal. They are the unexpected visitors in your code, each with its own unique characteristics and implications. These exceptions come in different flavors, each representing a different type of runtime mishap. Some are minor annoyances, while others can bring your entire application to a grinding halt. Understanding these distinctions is crucial for crafting effective exception handling strategies. By knowing what kind of exception you're dealing with, you can decide the best course of action to take. At the top of the hierarchy sits the throwable class, the grandparent of all exceptions. This class is the root of the exception hierarchy and is divided into two main branches, error and exception. Errors represent serious problems that are usually beyond your program's control. These are like catastrophic events. Think memory exhaustion or system crashes. Handling these is often not feasible, and your best bet is to let the program terminate. Errors are the kind of issues that you hope never to encounter. They are often indicative of a problem with the environment in which your application is running, rather than with the application itself. These catastrophic events can be caused by a variety of factors such as hardware failures, resource exhaustion, or even bugs in the Java Virtual Machine, JVM itself. When an error occurs, the best course of action is usually to log the error and terminate the program gracefully. Trying to recover from an error can often lead to more problems down the line. Exceptions, on the other hand, are more manageable and represent conditions that your program might reasonably be expected to recover from. They are further divided into two subcategories: checked and unchecked exceptions. Checked exceptions, as their name suggests, are checked by the compiler at compile time. These are exceptions that you are forced to handle either by catching them or declaring that your method throws them. Examples of checked exceptions include I/O exception for input-output errors and school exception for database errors. These exceptions are typically caused by external factors such as a file not being found or a database connection failing. By handling checked exceptions, you can ensure that your program can gracefully recover from these types of issues rather than crashing unexpectedly. Unchecked exceptions, in contrast, are not checked at compile time. These are typically runtime errors caused by flaws in your program's logic, such as trying to use a null reference or accessing an array element outside its bounds. Examples of unchecked exceptions include null pointer exception and array index out of bounds exception. These exceptions are usually indicative of bugs in your code that need to be fixed. Understanding these different exception types allows you to tailor your error handling strategies accordingly, ensuring that you're prepared for both the expected and the unexpected. By knowing what kind of exception you're dealing with, you can decide the best course of action to take. In summary, categorizing the unexpected visitors in your code is an essential skill for any Java developer. By understanding the different types of exceptions and how to handle them, you can create more robust and reliable applications. So the next time an exception rears its head, you'll be ready to tackle it head-on. Imagine a tightrope walker performing high above the ground. They are skilled and graceful, but there's always a chance of a misstep. The tightrope walker must maintain perfect balance, focus, and precision with every step they take. One wrong move, and they could plummet to the ground below. They are skilled and graceful, but there's always a chance of a misstep. This is where the safety net comes into play. The safety net is there to catch them if they fall, providing a crucial layer of protection. Without it, the consequences of a fall could be disastrous. That's where the safety net comes in, ready to catch them if they fall. In the world of programming, particularly Java programming, we have our own version of a safety net. This safety net is known as exception handling, and it ensures that our programs can handle unexpected events without crashing. In the world of Java programming, the try-catch finally block is your code safety net. It provides a structured way to handle exceptions, ensuring that your program doesn't come crashing down if something unexpected occurs. Just like the safety net for the tightrope walker, the try-catch finally block is there to catch your program when it encounters an error. It provides a structured way to handle exceptions, ensuring that your program doesn't come crashing down if something unexpected occurs. When you write code, you can't always predict every possible scenario. Sometimes things go wrong. Files might not be found, network connections might fail, or user input might be invalid. These are the moments when exception handling becomes essential. The try block is where you place the code that might throw an exception. It's like the tightrope walker attempting a daring maneuver. You write the code that performs the main task, knowing that there's a possibility something might go wrong. Try//code that might throw an exception. The try block is your first line of defense. It's where you anticipate potential problems and prepare to handle them gracefully. The catch block, as the name suggests, is designed to catch specific types of exceptions thrown within the try block. It's like the safety net, ready to catch the tightrope walker if they fall. Catch, exception type 1E1, / code to handle exception type 1. The catch block allows you to specify how to handle different types of exceptions. You can have multiple catch blocks to handle different exception types. Catch, exception type 2E2 / code to handle exception type 2. This flexibility ensures that your program can respond appropriately to various error conditions. You can have multiple catch blocks to handle different exception types. Each catch block is like a different part of the safety net, designed to catch specific types of errors. By having multiple catch blocks, you can handle different exceptions in different ways, providing a tailored response to each situation. / code to handle exception type 1, catch, exception type 2 E2, / code to handle exception type 2. Finally, the finally block is executed, regardless of whether an exception is thrown or caught. It's like the ground crew, always there to help the tightrope walker down, whether they had a perfect performance or a near misstep. / code to handle exception type 2. The finally block is executed regardless of whether an exception is thrown or caught. It's like the ground crew, always there to help the tightrope walker down, whether they had a perfect performance or a near misstep. Finally, the finally block is executed regardless of whether an exception is thrown or caught. It's like the ground crew, always there to help the tightrope walker down, whether they had a perfect performance or a near misstep. This block is typically used to clean up resources, such as closing files or releasing database connections. Finally, / code that will always be executed. The finally block is your last line of defense. It's where you ensure that important cleanup tasks are performed, no matter what happens in the try and catch blocks. This block is typically used to clean up resources, such as closing files or releasing database connections. Finally, it's / code that will always be executed. By using the try-catch-finally mechanism, you create a controlled environment for handling exceptions. Your program can gracefully recover from errors, log important information, and continue running smoothly even in the face of unexpected events. By using the try-catch-finally mechanism, you create a controlled environment for handling exceptions. Your program can gracefully recover from errors, log important information, and continue running smoothly, even in the face of unexpected events. This approach not only improves the reliability of your code, but also enhances the user experience by preventing abrupt crashes and providing meaningful error messages. Your program can gracefully recover from errors, log important information, and continue running smoothly, even in the face of unexpected events. In conclusion, just as a tightrope walker relies on a safety net to protect them from falls, Java programmers rely on the try-catch-finally blocks to safeguard their code. By understanding and effectively using these blocks, you can ensure that your programs remain robust, resilient, and ready to handle whatever challenges come their way.